Okay, Leaky Brains, we're going to do a podcast, and we're going to do the podcast on basically radiometric dating. Okay, what that is using basically a radioactive element or atom to see how old a fossil is. So we've talked about fossils. We're going to say, okay, well, a scientist finds a fossil, and they always say, well, this fossil is so many millions of years old, etc. And people kind of always wonder, how the heck do they actually know how old that fossil is? Okay, well, this is going to kind of lay it out to you in the most simplistic form that I can give it to you on basically how we radioactively date fossils. Now, one form that you probably are familiar with is carbon dating. Okay, most people have heard of carbon dating, and so we're going to talk about that using a carbon atom. Okay, now how do I know this is a carbon atom? You should remember from our biochemistry here. I have 6 protons. The black ones, they have positive charges. Now, this is carbon-12, C12. Now you'll say to me, C12, we just counted 6 protons. Okay, that's the atomic number. In this case, we basically list the atomic mass. There are multiple forms of carbon. Okay, the multiple forms of carbon, I'll write another word up here, are called isotopes. Isotopes. So if I'm talking about multiple forms of carbon, the atom, all of the different forms are isotopes of carbon. Okay, so in this case I drew carbon-12. It has 6 protons, 6 red neutrons, okay, and that gives us an atomic mass of 12, so it's carbon-12. Okay. Now it has 6 electrons. I didn't draw them in their different shells, I just put them out there. Don't worry about that. Okay. Now we're going to talk about a few key terms here. Isotope, half-life, unstable radioactive, okay, daughter isotope, and carbon dating is kind of what we'll talk about. Now here's what you need to know. This form of carbon is stable, so it's opposite of unstable or radioactive. It's not radioactive. It's stable. It's happy. It doesn't want to change. It's stable. Okay? Now, what happens, however, is some carbon, not very much, but some carbon has 2 extra neutrons in its nucleus. Okay, that's a big deal. 2 extra neutrons makes this carbon 14. It has 2 extra neutrons, 6 protons, 8 neutrons, carbon 14. Okay, carbon 14 is unstable. It's radioactive. Now, when I ask students in class, what's the first thing that comes to your mind when I say radioactive? They always say X-Men, Spider-Man, Superman, and many other, the plethora of basically superheroes. No. Okay, radioactive, when we're talking about atoms, basically means that they are unstable. They are going to change. Now, some radioactive isotopes we talk about are very hazardous. Okay, in this case, carbon-14, it's not really hazardous. Okay, about 2% of the carbon in all of your bodies is radioactive carbon-14. Now, the thing about carbon-14 is it is unstable and it is willing to change. Okay, in fact, it's going to change. Now, when you die, let's say we find a fossil, okay, the carbon-14 that is in that body when that fossil basically dies and gets buried is going to change. All right, and what it changes into is nitrogen. Now, how does that happen? Well, it's quite simple. All right, one of these neutrons basically gets energized and changes into a proton. Remember from biochemistry, if I add a proton to an atom, it changes the atomic number, it changes the atom itself. So this just became nitrogen-14. Okay, so my radioactive carbon just changed into nitrogen. I now have 7 protons, 7 neutrons. Okay, this is what basically happens with the radioactive carbon. Now, the daughter isotope is the new isotope. Okay, it's the new atom. So the nitrogen-14 is the new daughter isotope that the carbon-14 turned into. Okay, now, what is a half-life? All right. Scientists basically can calculate how long it takes for carbon to change into nitrogen. Okay? And so the half-life means the amount of time it takes for half of the radioactive carbon to change into nitrogen. All right? Now for carbon, it's about 5,700 years and change. Okay, we'll just say 5,700. In other words, okay, let's say I always start with 100%. Okay, I have a certain amount of nitrogen, or carbon-14, when the fossil dies, the organism dies, turns into a fossil. And so that percentage I have of carbon-14 is 100%. So after one half-life, I would have 50% of my C14, my carbon-14 remaining. Okay? After two half-lives, I would have 25% remaining. It's half of that 50. After three half-lives, I would have 12.5% of that original carbon-14 remaining. You get the drift? Every half-life that passes, I chop that number in half. Now, on the flip side, what we have to realize is all of my carbon is turning into nitrogen. So, in this case, let's say that I started with 100 milligrams of carbon-14. After one half-life, I would have 50-ish milligrams left. But I also would now have 50 new milligrams of nitrogen 14. Okay, every atom of carbon-14 changes into nitrogen 14. Okay, so if I start with a certain amount of carbon-14, after one half-life, 550 milligrams would be left. I started with 100, but I would now have 50 new milligrams of nitrogen 14. So I look at the two numbers, compare them, say what percentage is remaining, how many half-lives have passed. Now the easy part is telling how old the fossil is. Since I know that one half-life of carbon-14 is 5,700 years, if I have a 50-50 1-to-1 ratio of the carbon to nitrogen left, I know that one half-life has passed. So I know that that fossil is about 5,700 years old. Okay? If two half-lives had passed, I would have about 11,400 years that have passed. Okay? So I can tell how old the fossil is by looking at radioactive atoms, see how much is remaining, okay, that they originally would have started with, and then I can look at how much new daughter isotope there is to compare the two, make sure I'm okay. Then I can give a pretty dang good estimate of how old the fossil is by looking at the half-lives and how long it takes for half of the original radioactive isotope to decay into a new stable isotope, the daughter isotope. Okay? We call this absolute dating. It's pretty darn accurate, pretty close. Can I get it within the flippin' day and the hour it died? No. But if I'm this close, I can tell you how old that is. Okay? I can do pretty good. All right, so that's basically radioactive dating 101. The most simple form I can give you. Okay? Obviously, it's more detailed than this. Obviously, there's a lot more to it. I'm giving you the most basic knowledge that I can for the class right now. Okay? Absolute dating. It's great. Later.